Hello everyone, welcome to Ampere's law and its application, the third application due to a toroid. Now what is a toroid? Well, it's simply a solenoid bent into a circular shape. So here, this is basically a solenoid, meaning its magnetic field should also come as B is equals to mu naught Ni. So here, what we first do is find out the current enclosed by this. Now here, the current is the individual current in each of these turns. So in one current the current is this, and the other is this, and the other is that. So that means the current enclosed by this whole toroid will be the total number of turns into the current. Now what is the total number of currents? Now let's take the number of turns per unit length, which is total number of turns by unit length, which is n by here the unit length is the length of this whole toroid, which is its circumference, which is 2 pi r. So n is equals to n 2 pi r. So it is n 2 pi r I. Now here the line integral again this is equals to b dl cos theta, and like in the straight conductor part, here again the direction of magnetic field and the direction of this line integral, or just this line element, will be in the same direction. No matter where it is, they will be parallel, meaning theta 0 cos theta 1. So this is just b dl, and here b is constant, and dl it's just 2 pi r, since it goes from 0 to 2 pi r. Now let's use Ampere's law, which says that the line integral is equals to mu naught into the current enclosed. And now we can just put this back in here. So it's just mu naught and 2 pi r I. And here this and this is same, meaning that this and this is also same. So b into 2 pi r is equals to mu naught n 2 pi r I. 2 pi r cancels. Therefore, mu b is equals to mu naught Ni, which is exactly as that, because this is also a solenoid. And this is a short video today, and if you learned something new, please like and subscribe. Thank you.